Welcome to the class on Applied Computer Vision and Image Processing. Today we will discuss invariant feature extraction, and within this we will speak about two broad areas. One is detectors, identifying certain regions of the image like corners, blobs or points. We will also discuss extraction of descriptors or features at these regions. We will then speak about feature point matching algorithms. Let's begin by looking at motivation. Why we need to do invariant feature extraction? What are the applications where this is useful? For instance, let us say we want to create a panorama image. In a panorama image, you take multiple photographs of a scene, possibly with some overlap in the area. Right? For instance, there is some overlap between these two photographs. Similarly, there could be other photographs which have overlaps in between them. And then you would want to create a single image by stitching these areas. When you perform this operation, you not only have to understand the geometric properties of the camera, but you also need to be able to estimate what is the region where there is an overlap. For instance, the system needs to automatically determine that this is where there is an overlap between the two images, but there is no overlap between these parts. So the extent of overlap needs to be determined. So this can be done by extracting features that are consistent across images. Now you may not notice a significant change between these two images, but there is a slight change in the lighting. So when you rotate the camera from this angle to this angle, the way in which light gets incident on the lens will change. The kind of background lighting will change. So you need to extract features from this portion and this portion which are invariant to these lighting changes. Similarly, there might be slight variations in the camera due to which there might be some jitter between this image and this image. There might be a slight movement of the camera such that this and this image are vertically also translated with respect to each other. You again need algorithms that not only handle this horizontal translation but also the vertical translation, and they're able to figure out where a particular pixel in this region is located in this image. This is an application where we want to match the reference printed circuit board, which is this image, with a test printed circuit board. The test board could be on a conveyor belt, or it could be placed at an angle to the camera. So in order to match this board with this board, we would need to rotate and correct for the scale variation between this image so that it lines up with all the components in this image. To do this, we studied that we would need three sets of points which are corresponding to each other. So for instance, this point in the reference board corresponds to this point in the test board. This point in the reference board corresponds to this point in the test board. This point corresponds to this point. After finding these points, we would be able to solve for the homography and get this matrix using which we can rotate or translate, or rather perform a transformation on this image so that it lines up with this image. But the problem still remains, how do we obtain these correspondences? These correspondences can be predefined. It can be obtained using fiducial markers on the printed circuit board. It can be obtained by placing certain barcodes. But in general, you can also obtain this by using invariant feature points. Invariant feature points will tell you that there are certain regions in this image which are exactly the same as regions in this image. In this image, you can see that certain points have been marked out. These are also marked in this image as well. These points are scale invariant feature transform points, which we will study in the subsequent slides. Let's zoom into the image and see some of these points in detail. For instance, we are zooming into this area of the reference board and this area of the target board or the test board. Let's look at this area. So you can see these points have been highlighted in the form of circles. Let us look at the components in these zoomed in areas. If you look at this component, this is the same as this component. Similarly, this component is the same as this one. This is the same as this. This white color box is the same as this white color rectangle here. and this white rectangle corresponds to this one. And if you notice, there are points on all of these components. So for instance, there are points on this component, and these match up with the points on this component. There is a point at the center of this component, and there's a point at the center of this component as well. Of course, there are additional points on this component, but that is because this image is bigger in size than this one. Similarly, there is a circle, or rather a feature point at the center of this component. There is a feature point at the center of this one. There are feature points at the corner of this rectangle, and there is a feature point at this rectangle corner. There are feature points at the corners of this rectangle, and there are feature points at the corner of this rectangle as well. Similarly, this particular marking, there is a feature at the center of it, there's a feature at the center of this marking as well. So you can see there are a lot of feature points that correspond to each other, but there are also many feature points that do not correspond with each other. In the subsequent slides, we'll study how to extract these types of feature points. We also need to match up these feature points. Let us see how this is done. For instance, here we are showing that the reference printed circuit board has been matched with the target printed circuit board using only some of the points that had been extracted. Notice that all the points have not been matched. A few of the points only have been matched. And using these matches, the homography matrix is recovered, and the reference board is overlaid over the test board. Let us look at a few sample matches in more detail. So again, we've zoomed into a part of the image, this part of the image. So you can see that one of the points here near the white rectangle has been matched with a point on the white rectangle in the test board. Similarly, a point from this component here has been matched with a point in the test board. A point on the reference board located here has been matched with a point here on the reference board, and so on and so forth for all the other components as well. Look at this component. This component has been matched with this component. We also see that several of the feature points that were extracted have not been matched. For instance, there were several feature points in this area which have not been matched. There were a few points that we had discussed in this particular white rectangle. Those have not been matched. So the matching algorithm automatically picks some of the feature points and uses the correspondence to generate the homography matrix. And we'll discuss this also in more detail in the subsequent slides. The process of extracting feature points and feature descriptors and matching them can be used in various kinds of applications. Here we are seeing an example of a document which is being matched with its digital copy. You can see that the document is badly skewed, and there are crumples also on the paper. But even then we get a successful match. This is an example of matching an outdoor scene to create a panorama. These are two different images of the same scene. Point correspondences are found here, and using these point correspondences, the two images can be stitched together. And these kinds of matching algorithms and feature point extraction can be invariant to affine transform, non-affine transform, and lighting or camera variations. The technique of feature point extraction that we study will fall into the broad category of corner detectors. For example, in this image, the red color dots show corners in the image, distinctive corners of different objects in the image. Blob extraction. So here we can see blobs have been extracted from this image, and these blobs are all of different scales. And feature point detectors. We will also study descriptors that describe various image features near these detected locations. Let's look at some of the properties that we expect from these features. In order to implement some of the applications that we have discussed so far, the features would have to have invariance to geometric and photometric changes. So for instance, whether an image is scaled, rotated, translated, or the illumination in the image changes, the feature points must be obtained at the same location. So for instance, let's say this is an image of an outdoor scene. These are 4 example feature points that have been extracted. This is a rotated version taken by altering the camera slightly, but the view is the same. So the camera has moved while taking a picture of the same structure. If these are the corresponding points that are obtained, then there would be no chance of matching these points, because these points are from different locations. The only matching point is this one. If you notice, this point, and this point are from different locations in the image. They are not at these three locations. Whereas, if you obtain these 4 points from the image, there is a chance that you will be able to find a correspondence between this image and this one. In addition, the feature points must be compact in nature. What this means is every pixel in the original image cannot be an important feature point. That would just mean that you're comparing every pixel in the image point by point. That does not make any sense, because all parts of the image need not be invariant to scale, rotation, translation, illumination. There will only be a few locations in the image which are invariant to these changes. So the features that are extracted must be fewer in number than the total pixels in the image. The third property that we are interested in is saliency. The features must have some saliency, that is, they must represent certain important properties of the image or the region surrounding the feature point itself. Thus, the description of this region surrounding the feature point may be compared with the description of the image region surrounding this feature point. And this will allow you to do a comparison between different feature points in the image, and therefore helping us identify which points correspond to each other. Now that we have covered a few applications, let us look at how detectors and descriptors are extracted. Before we start the algorithms proper, let's intuitively understand the characteristics of good features. If you want to do any image perception, a lot of the information in an image is redundant. So for example, look at this image. Most of us would be able to guess that this is a cat. You don't really need to know that there is a lot of fur, the whiskers are gray in color, the eyes are brown in color, in order to infer that this image is a cat. Yes, this image gives you additional information that this is a gray color cat, the eyes are brown in color, and so on. But this information itself is not required in order to analyze that this is a cat. However, striking a balance between what is sufficient and insufficient information is non-trivial. Let's look at an example to understand that. Let's say we were given this outline. Will we be able to guess that this is a cat? Not really so, but if we were given additional information, for instance, one of the edges is extended, right, and some additional lines are drawn, you would be able to infer that this image is a cat. But drawing the same inference from this image is not possible. So yes, you have to strike a balance between what is sufficient and what is insufficient. This may be too much information. This information is sufficient, but this is too little information. So you have to extract information that is concentrated at contours, that is regions where the color changes abruptly. And you have to identify such regions in order to be able to recognize an image or handle the task of image perception. Now we will discuss the Harris corner detection algorithm. It was published in 1988 and continues to be a popular technique for identifying key properties in an image. It's based on the intuitive understanding that the image gradient around a corner has multiple dominant directions. So if there is a strong edge present in an image and this edge meets another edge, then that meeting point is a corner, and at that corner point the gradient around it will change in multiple directions. Corners are also repetitive and distinctive. That means if you take an image with a camera from one view and then you move the camera slightly, the corners will still be visible in both the images. They will be distinctive and they will get repeated in both the images. The strategy for finding corners is take a window and move this window over the image and find locations where the gradient changes in 2 or more directions. Let's take an example of this input image in which we want to detect a corner. To do this, we will start with the location x, y, place a window around that point, and compute this difference function. The difference function takes this location I, x, y, and moves a window around that and computes this sum of differences. The sum of squared differences would change significantly if you move away from the corner. If the point x comma y were on an edge, this sum of squared differences would change significantly only if the window is moved in this direction. But if the window is moved vertically, the sum of squared differences would not change significantly. Similarly, if the point was on a horizontal edge, the point x comma y is on a horizontal edge, moving the window vertically would lead to significant changes. Horizontal motion of the window would not lead to any changes in this function. And if this window or the center of the window x comma y, the location would be at the center of the image or inside this dark area, then this difference would be 0. Similarly, if this point were in a bright area of the image, uniformly bright area of the image, this function would again be 0. Using this intuition, you can determine where there are strong corners present in the image. Note that this property would be true even if the object was to be rotated in different directions. So for instance, here this corner would exhibit the same property, that the sum of squared differences would change significantly when you moved the window away from it. Ditto for any point on this edge. Moving along this direction will not lead to a significant change, but moving along this direction will lead to a significant change. Again, true for this object. Intuitively, we understood that corners can be detected using the sum of squared difference operation. The Taylor series expansion of the intensity or the value of the image at this location x plus u y plus v can be given in the following way. I of x plus u y plus v is equal to I of x comma y plus u times change of the image along the x direction plus v times change of the image along the y direction plus higher order terms. If the window moves by a very small amount, the values of u and v will be small and the higher order terms will be insignificant. They can be ignored to get an approximation like this. The change of the image or the gradient in the x direction and the gradient of the y direction can be used to get a matrix representation like this. And in turn, the change can be represented using ix and iy, and you get a term which is in this fashion. Substituting this in the equation of sum of squared differences will give you this equation, which can be written in this fashion. The sum of squared differences can further be expressed in this fashion using a Hessian matrix. And in further discussions, H will represent the Hessian matrix. Intuitively, what we are doing is we are taking a location x comma y and we are moving or searching for a small location around x comma y and determining if during the search is there a significant change in the value of the sum of squared differences. If there is a significant change in this value, that would indicate either an edge or a corner. And the potential directions in which there will be a significant change to this expression E can be found by analyzing the eigenvectors of the Hessian matrix H. How do we find the eigenvectors of H? Going by elementary linear algebra, we will have Hx equal to lambda x, where lambda are the eigenvalues and x are the eigenvectors. And the eigenvalues can be found by setting the determinant of H minus lambda I to be 0. And in our case, H is the Hessian matrix, and setting this to 0 would mean setting the determinant of this matrix to 0. And lambda therefore can be these values. So there are two values of lambda, one would be the smaller value and another would be the larger eigenvalue. Once the eigenvalues are obtained, we can get x by solving this function. The larger eigenvalue of E, let's say, is lambda plus, and the corresponding values of x plus are x comma y, then that means that shifting in this direction, shifting in the direction of x plus, would give you the largest change of E. Similarly, if the smaller eigenvalue is lambda minus and the corresponding shift is x minus, or the eigenvector that is obtained is x minus, then moving in x minus will give you a smaller value of E or lead to lesser change in the sum of square differences. Now, how do the eigenvalues allow us to identify corners? Let's assume that this was our input image with a white area and a gray area. And there's an edge which has been highlighted in black color between these two. For points that lie on the edges which are present in the image, like for instance these points, one of the eigenvalues will be comparatively larger than the other eigenvalues. For points that are on corners, like for instance this point, both the eigenvalues will be large. Now, in order to find these kinds of points, what you could do is you could select a threshold and you analyze the smaller eigenvalue of every point in the image. If the smaller eigenvalue is larger than a certain threshold, than the threshold that you have selected, you can assume that that's a corner point. Another strategy could be analyze a small neighborhood of points. If the smaller eigenvalue of one of those points is larger than all the neighboring eigenvalues, then that could indicate that that particular point could be a corner point in that area. This analysis can also be performed using the corner response function. The corner response function R is defined in the following way, where alpha is a constant between 0.04 to 0.06, and this is manually selected. You can analyze R in the following manner. If R is less than 0, then it indicates that the particular point that you are looking at is most likely an edge point. If R is greater than 0, then it would indicate a corner point. And the magnitude of R will determine how strong the corner is. Similarly, if R is a relatively small value, then that indicates a flat region or a region that has either completely uniform white or uniform gray value. In this way, using the eigenvalues or the corner response function, one can detect where corners are present in the image. So how do we put all of this together? Given input images, you compute the corner response function. You visit every pixel in the image, compute the Hessian at that pixel, and get the corner response function using the eigenvalues. Once you compute the corner response function, you take a threshold, select all the points where the corner response is greater than a particular value. Once you find several points with the corner response function greater than a certain threshold, select only those points in a particular region which have maximum in comparison to all the other points in that area. So for instance, these points which have been selected have maximum corner response function in comparison to all of these functions in this area. In these two images, you can see the final Harris corner points displayed in red color. So for instance, here you have a few points. There are some points on the nostril here. There are 3 points on the mouth. There are some points in this black colored area. And if you notice, in this image also, points appear at similar regions. So for instance, there's a point here and there's a point here. There is a point in this particular area and there are several points in that curve. Similarly in this region. And so on across the entire image. There are a few points here, you can see a few points here. On the hoof as well, you can see some points here and those are repeated here. The corner response function is invariant to rotation. The reason being, even if you take an input image and you rotate it, the gradients might change direction, but the magnitude of the gradient would not change. Therefore, the eigenvalues don't change, and the corner response function depends only on the eigenvalues. Whereas if you scale an image, the gradients along the edges will all change. This particular point may be detected as a corner, but if you scale it, the same point would appear as an edge. In effect, the Harris corner detection algorithm is invariant to rotation, but it varies if you scale the image. In summary, the Harris corner detection algorithm is able to capture good corners which have high contrast. and it is also capable of ignoring edges. It depends on the principle that at corner points, the gradients of an image change sharply when you move a window in all directions. It also indicates that the Hessian matrix at a corner point will have two large eigenvalues. We will now discuss scale invariant blob detection. We saw that the Harris corner point detection algorithm could detect corners that were invariant to rotation, but if the image is scaled, then the same points are not obtained. For instance, take these two images. This one is the original and this one is a close-up of this object. Can we detect same features in both the images? More specifically, the goal of scale invariant blob detection is to detect blobs that occur in both the images. This is also referred to as automatic scale selection. And how do we achieve this? In a nutshell, we identify a scale that gives you local maxima of some function f in both of these images. And the Laplacian of Gaussian is such a function. A few slides ago, we had studied that the characteristic of good feature is to capture variations or sharp changes in the image. The blob detection algorithm is also based on this concept. The scale invariant blob detection algorithm also depends on extracting regions of an image that have strong changes. Let us use a 1D signal to understand this concept. Here you have a signal which has a sharp transition at time t equal to 1000. A Gaussian kernel has been taken to smooth this signal out, and you get this result. When you compute the first derivative of the convolved result, of the result of taking the convolution of the Gaussian with the signal, this is the result that you obtain. There is a strong impulse at time t equal to 1000, which is where there was a transition in the signal, or there was significant information change in the signal. A similar effect can be obtained by using the Laplacian of Gaussian at various scales. The initial idea was to convolve with Laplacians at several scales and find the maximum in the scale. So you take the original signal and convolve it with a Laplacian signal at various values of sigma. And this would be the response. However, the Laplacian decays as the scale increases. For instance, if you increase the standard deviation and compute various Laplacians, this is what you get with a sufficiently large standard deviation. So instead of using unnormalized Laplacian response, you would use normalized Laplacian response. Now, given this original input signal, instead of taking a convolution with the unnormalized Laplacian signal, if you take a convolution with the normalized Laplacian signal, which is like this, you would get the following result. This is the result with the unnormalized Laplacian. This is the response to normalized Laplacian. You can see that the original signal has a time period of 8, and the Laplacian has a significant response, has a very high response at standard deviation equal to 8. There is a good response at the other standard deviations also, but the maximum response has been obtained when the standard deviation is 8. Therefore, this would be considered as the characteristic response or the scale for this signal. In the case of a two-dimensional signal, the Gaussian kernel would be defined like this, and the convolution is indicated with this formula. G is equal to I, which is the input image, convolved with the Gaussian filter having a specific sigma or standard deviation, and these would be the filter values. The Laplacian of Gaussian is defined in the following way. The convolution is indicated using this formula, where L is equal to the input image convolved with a Laplacian signal at the standard deviation sigma. These are the kernel values of a Laplacian signal, which is a 5 by 5 kernel at standard deviation equal to 1. And these are the values of a Gaussian kernel, 5 by 5 kernel at standard deviation equal to 1. These are the images obtained after applying normalized Laplacian of Gaussian on top of this input image. The sigma for these images has been set to 1.1, 1.3 and 1.5. Dark regions in this image indicate negative results, and the brighter regions represent the positive locations where the image has a positive value. And at the bottom you have 0 crossings of the corresponding images. The bright regions in the 0 crossing indicate edges, and the dark regions indicate the background. Let us look at how the Laplacian of Gaussian is applied on images. This is an image of an outdoor scene. This is the same image taken at a closer distance. You can see that this has greater resolution, or this appears zoomed in. Taking an LOG at a particular standard deviation, at this point, you get this response value. The LOG at the same location in this image, the zoomed in image, is this. The Laplacian of Gaussian taken on this image with an increased standard deviation at this location is this value. The response of LOG on this image at the same location is this. The standard deviation has increased further. The LOG with the increased standard deviation is taken from this point, and the response is plotted here. The LOG on the zoomed in image for the increased standard deviation is taken from this point and is plotted here. With further increase in the standard deviation, you start seeing a dip in the response. So for instance, the response of LOG at an increased standard deviation from this point is plotted here. And the response of the LOG from the zoomed in image for the same standard deviation is plotted here. And if you keep increasing the standard deviation and plotting the LOG response from this image and this image, the result that you get is as follows. For this image, as you keep increasing the standard deviation, you'll see that the response peaks at a particular location and then starts going down. That is, for a very large standard deviation, the response is really low. Similarly, for this image, the response from LOG peaks at this particular standard deviation and then it dips off. So the characteristic scale or the automatic scale extraction for this image would be this standard deviation at this point, and the automatic scale for this particular point would be this value. The characteristic scale for every point in an image can be extracted separately. So for instance, at these 2 points, for this image the characteristic scale was here, and for this image the characteristic scale is approximately sigma equal to 10. For this image, which is of sunflowers, the characteristic scale of the point at the center of the image, that is this particular point, is shown here. It's approximately equal to 2.5. And the characteristic scale for this image for a point located at the center over here is approximately 4.5. And notice this image has twice the resolution of this. So putting it all together, given an input image, we take every point in the input image and apply the Laplacian of Gaussian response at that particular point. And we determine what is the scale or the sigma in which you get the maximum response. So for instance, this particular point in the image and this particular point in the image respond best to this value of sigma. A different point in the image, let's say this one, might respond to this particular Laplacian of Gaussian. A different point, let's say this one, might respond to a totally different sigma value, and so on. And for every point in the image, we'll be able to extract different characteristic scale or automatic scales. Using the response of LOG on the image at different points, we would be able to identify blobs or characteristic shapes in the image. This is an example of a sunflower field from which blobs have been captured. And because the LOG is invariant to lighting, even if you change the lighting of the image, the same blobs are obtained. This method of blob detection was published first in 1998, and it was shown that the detection algorithm is invariant to various kinds of noise, to scaling and also to rotation. We have completed the discussion of corner and blob extraction. Now we will discuss invariant feature point extraction. Invariant feature point extraction was first published by Lowe in 2004. The intuition behind this is that the Laplacian of Gaussian can be approximated by using the difference of Gaussian. We will recall from our definition that the Gaussian of an image is defined as capital G sigma equal to the image I correlated with the Gaussian filter. Similarly, the Laplacian of Gaussian image is given by the image L, which is equal to the image correlated with the Laplacian filter, which is defined here. The difference of Gaussian in image terms would be defined in the following way. Difference of Gaussian at k sigma is equal to the Gaussian of the image computed with the standard deviation equal to k times sigma minus the Gaussian obtained with k minus 1 times sigma. In this slide, we show an input image that has been correlated with a Laplacian of Gaussian filter, a 7 by 7 Laplacian of Gaussian filter at 3 standard deviations. So this is the result of applying a Laplacian of Gaussian filter at sigma equal to 1.1. This is the result of applying a 7 by 7 LOG filter at sigma equal to 1.3, and this is the result at standard deviation equal to 1.5. These are the corresponding zero crossings. This is the zero crossing obtained from this LOG image. This is the zero crossing from this image, and so on. At the bottom, we have computed difference of Gaussian images taking a 7 by 7 Gaussian filter at the same standard deviations. This is difference of Gaussian computed at standard deviation equal to 1.1. This is at 1.3 and this is at 1.5. Let us now see how feature point detection was implemented in the 2004 paper. An input image having a size m by n, that means m rows and n columns, is considered to be I0 or the first octave. This first octave is subsampled to obtain a second octave or the image I1. The second image will have number of rows equal to m by 2 and number of columns equal to n by 2. That means for every 4 pixels in this image, there will be 1 pixel in the image I1. Similarly, the third octave will be an image that has been created from the second octave. The third octave will have a size of m by 4 and n by 4 columns, and it is referred to as I2. And the fourth octave is an image which is created from the third octave. The size of the image is m by 8 rows and n by 8 columns, and the index of the image is I3. The difference of Gaussians are now computed from the different octaves in the following manner. For example, this is the first octave or the image I0. Gaussian filters with increasing standard deviations would be applied to get 4 different images from this image I0. For example, we may choose to apply a 7 by 7 Gaussian filter with sigma equal to 1.5 to obtain this image. Similarly, a 7 by 7 Gaussian filter with sigma equal to 3 is applied on I0, which is this image, to obtain this image. Similarly, a 7 by 7 Gaussian filter with sigma equal to 4.5 is applied on I0 to obtain this image. And sigma equal to 6 with a 7 by 7 filter would give you this result. Now at the bottom we can see difference of Gaussians. The difference of Gaussians are obtained by subtracting the filtered version, that is this image, from image I0. Similarly, this difference of Gaussian is obtained by subtracting this image from this version. This difference of Gaussian is obtained by subtracting this image from this one. And this difference of Gaussian is obtained by subtracting this image from this image. Visual inspection of the difference of Gaussian will tell you that certain features in the image are clearly visible in some of the difference of Gaussians, but certain features are not visible in all the DOG images. So for example, if you look at this corner is present in all the 4 DOG images. So it's present here, 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 and in the fourth DOG. But the corner corresponding to this alphabet is visible only in these two difference of Gaussians. It's barely visible in this difference of Gaussian, and it is not visible at all in this DOG image. Similarly, this corner is visible in all four DOG images. But the corners corresponding to these alphabets are visible in these two difference of Gaussians, barely visible in this one, and not visible at all here. Intuitively, features that are consistently visible across a majority of the DOGs indicate characteristics of the image or regions of the image that are consistent across a wide variety of variations. That is, even if the image is scaled or the image illumination changes, these points might still appear across DOGs. This process of looking for points gets repeated across multiple octaves. We've just seen that this is done over octave I0 or the first octave. The same process would be done on the second octave, the third and the fourth octave. To put it all together, the following steps are done for every octave. For each octave image, Gaussian filtered versions are extracted with increasing standard deviation. For example, sigma, 2 sigma, 3 sigma and 4 sigma, where sigma is manually selected. You then select 3 consecutive difference of Gaussians. So for instance, you might choose to select these first 3 difference of Gaussians or these 3 difference of Gaussians. You loop through every pixel in the central difference of Gaussian, in this difference of Gaussian. For example, if the sets that you picked are these 3, let's say this DOG, the second DOG and the third DOG, then you would select the central DOG as the image through which you would loop. Let us assume that in one iteration we selected these 3 difference of Gaussians. We are going to zoom into these 3 difference of Gaussians and arrange them in the following way. This DOG image is placed here for clarity. This DOG image is placed here, and this DOG image has been placed here. Now we loop through every pixel in this DOG image. So for instance, we loop through each pixel here. And for every pixel in the central DOG image, that means for every pixel in the central DOG image, we compare its value with the 8 neighbors in this image, the 9 neighbors in this image, and the 9 neighbors in the next DOG. So for example, let's say this was the pixel that you're considering. You will compare the value of this pixel from this image with its 8 neighbors and the 9 neighbors from the previous DOG, that means this DOG, and the 9 neighbors from the next DOG, that means this DOG. And if the value of this pixel is less than these 27 or it is greater than the 27, then it is selected as a local extrema point and it is marked on image I0. This process is done for the second set of DOGs as well. So for instance, you would select this as the central DOG, that means you would place it here, and this as the upper DOG and this as the lower DOG. And you would loop through every pixel in this image to find out which of the pixels has a value greater than its 27 neighborhoods. And then this is also marked on the I0 image. This process is repeated for all the other octaves as well to select the extrema points. This slide illustrates that the process of selecting local extrema points is repeated on the second octave as well. So for instance, we had discussed how the first octave or the image I0 is processed by applying Gaussian filtered versions with increased standard deviations. The difference of Gaussian images are examined to obtain local extrema points. The same process is done on octave I1, I2 and I3. One may wonder why 4 standard deviations or scales and 3 difference of Gaussians have been selected in this process. Why not use 5 standard deviations and 4 difference of Gaussians? A database of several images was used to perform empirical studies, and the scales and number of octaves were based on the result of that analysis. So for instance, this graph shows the number of scales or the number of standard deviations that were sampled for every image octave, and the number of points that were correctly matched in this database. And it's seen that the number peaks when we get to 3 scales. So when we select image points or local extrema points after analyzing 3 standard deviations or 3 difference of Gaussians, we obtain good matches. Similarly, the number of key points obtained per image as a function of octaves is shown here. So once you go beyond 4 octaves, the number of incremental key points that are obtained are not that significant. So a decision was taken to use 4 octaves. Now that we have discussed detectors which identify corners, blobs and points, let's discuss descriptors which describe the image region around these points or corners and blobs.